Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Yeah, imagine a big audience. Okay, so it's a pleasure to be here, my first visit here, and I'd like to thank Jianfeng for inviting me. And so here I'll present some work jointly with my student Peng Zhao. Basically, we have two papers. One is the algorithm, one is some theoretical result related to Lasso. And so first I'd like to make a case for why we need feature selection and why computation is very important, which I think for this audience, I don't need to say much. And the second part, I want to make a contrast between automatic selection and more subject knowledge based. And of course, today I'm talking about automatic selection. And we try to avoid the combinatorial search like in-model selection criteria like AIC, BIC, and use this L1 penalized loss function approach. And the first result I'll present is not to do with the algorithm, but just more talking about, suppose you have fixed number of features and you have number of samples going to infinity, whether BLasso or not BLasso, like Lasso will actually select the correct features. Because the model selection criteria like EIC or BIC, people have shown that in that case will pick the right ones asymptotically. So the question is now you make a computational shortcut to this L1 penalized loss function, would you lose that property? And it turns out that you do lose a little bit because for some designs, you won't get consistency. And the last bit will be on the algorithm. So we have an approximate algorithm to solve the Lasso problem for different smoothing parameters in one sweep. So this is taken, I just wrote an overview paper on IT and statistics. And if anybody interested, I'll be more than happy to send to get comments. So in that paper, I basically divided statistics problem in IT areas into three big chunks. The first is where I think this Microsoft group very familiar with, which I'm learning about information retrieval, information extraction, natural language processing, and web search. And the second cluster is used to be a computer science hardcore, like architecture, chip design, programming, and even network monitoring. And I work on network tomography, and colleagues of mine from a CS department work on using machine learning technique to do program debugging. And the last part, actually, my group has been working on more, is this I call fringe areas. All the other science engineering areas which are impacted by IT. For example, we've been working on remote sensing, and my colleague work on astronomy, neuroscience, and finance. But they all, from the statistical point of view, share a lot of common features and have the same problems in terms of high-dimensional data and speed of computation. So again, this is very much a statistician view of IT problems. From where I stand, I see that there are all these new forms of data which we're not used to before the IT revolution, like text data. For example, if you give my student PowerPoint documents, they cannot quite process yet, right, unless they pick up some language skill. We are used to numerical data already in vector form, matrix forms. And you have images, which we deal with. Seems easier than text for us because it's very regular, just numbers in big matrices. And video, I did some audio compression. And all of these different forms are high dimensional, and a lot of applications, you have this online demand. Data comes in high rate, and you cannot take a few hours to process it. Like in the remote sensing application I've been working on, definitely it's the case. You want the data come down from the satellite, you want to process online instead of store it and take many years to process it. And of course, as a statistician, I see that statistics is at the center of all these activities. And I'm just going to run through, like I see as typical statistical analysis. Now there are a lot of challenges. So even from data processing, you have to know how to deal with database, and you have to have some better programming skills than MATLAB usually to really process the data. And a lot of times I deal with like data compression. For sensor networks, you have this computation of storage, transmission, and computation competing for the same battery power. So you have to integrate the compression concern together with analysis. And a big part of success for classical statistics is this exploratory analysis, kind of started by Tukey, basic visualization of data. And now it becomes extremely difficult because the high dimension and just the sheer volume, and just we only have 2 dimensions most of the time to view them. And really, as I was talking to Jian Feng and Sumi, that the data we're looking at, we don't know how to visualize it or to have a sense out of it. But on the other hand, you do have this multimedia representation, which we didn't have. So you do, and also we can run more models. Maybe you should run some models, and the result of the model can be presented, and feed a simple model and look at the model instead of the whole data. So you do have this power of computation and the multimedia presentation. So you have some advantages, but a huge volume of data presenting the most difficult obstacle. And static modeling for machine learning or for people in IT, this is very common now. We really base a lot on loss function and a lot of additive model, either in the transform domain, the original domain, and we rely on either cross-validation or test data to do a validation. The more classical statistical concept like confidence intervals, p-values, things like that, we just don't use a lot, because all those what it means doesn't really make sense anymore with such a huge volume of data, the way we process it. So the question is there something we just can do without, or actually something we need to bring back? But doesn't matter what your problem are. Everybody's talking about, you need fast computation, and you have to do some form of feature selection or data reduction. And if you look at the tradition started with R.A. Fisher, basically feature selection was best, mostly done based on subject knowledge. And even with the modern IT problems, like the remote sensing problem, where we have multi-angle satellite images in the Arctic region, and we have basically for each pixel 36 dimensions, and we want to find out where are the clouds. And it's very important for energy budget calculation for this atmosphere science, like whether the temperature is going up or how much radiation we're taking from the sun. And they usually, in their model, they have to put where are the clouds to do the calculation. And in the polar region, it's extremely difficult because white on white, and the temperatures are also very low on the ground. And therefore, there's this NASA satellite called MISR, which has 9 angles. It's like a stereo. So you see that use the stereo effect can separate clouds from Arctic ground. And in that case, I had a student who now graduated, worked for like 3 years with NASA, the JPL group. And we basically end up talking to them a lot, doing plots, and we end up from 36 features, we reduce to 3 features. Okay? And we end up using something very simple like thresholding and the features quadratic discriminant analysis. So very classical stuff, but still solving modern problem, but it's 3 years, right? Lots of back and forth. Where you're tapping into the human brain, right? Get subject knowledge out. And here I want to talk about that in cases where you don't have the luxury of prior knowledge, or you don't have the access to experts, or because time constraint, we still do a lot of automatic feature selection. So that's the topic of today. But I want to put a plug for this subject-based feature selection. And I think if you have the time, you have the resource, usually better than automatic selection. And the feature selection or variable selection, the field started in the early 70s by Akiiki, like engineer, and statisticians like Schwartz did BIC, and Reasoner, another engineer. People recognize that you cannot do maximum likelihood estimation when you have bigger and bigger model. You end up with the biggest model, therefore you don't have good generalization error. So they formulate this through this model selection, which is a combinatorial search. We were faced with that problem with a bioinformatics problem with a former student, Rebecca Yostan. And there the problem is you want to classify some tissue into cancer or not cancer. And you have the features are the different gene expressions through microarray technology. And usually you have 6,000 genes, so features like 6,000 dimensions. You only have n like 50, 100 like samples. And we did some pre-selection, and we end up with like 100 or so. And if you do a model selection on that, you're going to have to go through like 10 to the power 30 possible subsets. First, it's not computationally feasible, and also we don't believe that the data have that power to differentiate between these models. So either way, you shouldn't do that. And alternative is to avoid this combinatorial search and do a continuous embedding to a convex optimization problem like boosting, and which I call a third-generation computation method in statistics or machine. I think machine learning is really part of modern statistics.
So can you talk about
Yes.
What do you call the second generation skills? Learning some history.
Here you go. It's my terminology.
Okay.
The first generation, what I call, hasn't caught on yet, is that we didn't need a computer, right? You went for a closed form solution. You look at Bayesian statistics, conjugate priors. For a long time, that's what you can do. You have closed form solutions, so fast or not fast, you don't need computers. And we're constrained with those models. Bayesian statistics definitely were very much constrained until like MC really kicked in. And the second generation is like that's the time I was growing up as a statistician, that you design statistical criteria. Something going on? That you don't worry about calculation. You design, you prove asymptotic results, and then you throw it into an optimization routine, and you worry about that later. You don't think about it. You just do your mathematics. And it worked for a while, right? In the 80s and the 90s, statisticians didn't really have to worry about it. But now with the huge size of data, if you don't worry about computation, you basically cannot even find out how your procedure works. So that's what I call third generation. So a lot of the machine learning technique like SVM and boosting very much with that in mind in the design. And it's way like MC too, right? If an MC algorithm doesn't converge, you probably doesn't want to use that prior. So computation becomes the first requirement. And boosting for this crowd, how many of you have heard about boosting? Yeah, so I'll go fast. So it was quite interesting that it was not started as a very practical algorithm. It was first started by Shapiro in his PhD thesis in 1991 to answer a pack learning conjecture bivalent. The question was, can you combine weak learners so that to drive the training error to zero? It was very theoretical. And 1996, AdaBoost appeared. So that was the first practical algorithm by Freund and Shapiro. And from that time, my understanding that boosting together with SVM, a lot of data set, a lot of empirical results show that they are kind of neck-to-neck good results for different cases. And what got me interested in boosting actually in the beginning was this empirical success, kind of peculiar why it's so successful. It was also this coupling of computation and regularization. So boosting is like you start with a base procedure like a weak learner, and you don't modify the procedure like a lot of time in statistics. You modify your data, but then you apply the same procedure to a modified data, residuals, or resample data, and then you combine the results. And that turned out to be a lot more flexible than tuning a particular procedure. And an interesting phenomenon there is that it doesn't really want the procedure to converge. You actually want to stop early. And of course, stopping early was also used in neural nets, right? It was not the first time. But that was not the convex optimization problem, so it was much harder to analyze. So, and that was really from the learning. And there was a big step forward connecting with optimization for AdaBoost, and therefore all different versions of boosting is this gradient descent point of view of boosting. And if you think about that, you don't have to stick with the exponential loss function on the margin. You could do other loss functions. So the good old regression comes back with L2 boosting, right? Because then, in this case, you actually just fitting residuals. You're not really resampling anything. And here you can see that nothing's new, and refitting of residuals was already proposed by Tukey 1972 for time series analysis. So you take the first kind of big high-level features out, and then you get finer features for residuals. For boosting, the number of iteration steps is the regularization parameter. And at a high level, many of us probably all believe that there's an intrinsic connection between regularization and computation complexity. But really, how they exactly relate, we still don't know. And boosting, for me, provided this very explicit link. You actually looking at the regularizing parameter is an optimization parameter. And also to our surprise, in a paper in JASA, Peter Buman and I had, we said that, well, boosting was basically coming from the computational end of statistics. If we subject it to some theoretical analysis, like if you look at non-parametric statistics, after fish information, we have this framework called minimax optimality. So you say that my true function falls into a smooth class, and you ask yourself, what's the fastest rate you can estimate this function in the minimax sense, the worst case. And that has been a kind of benchmark to compare a lot of non-parametric procedures. And we said, well, let's analyze boosting in the L2 case, because mathematics is easier than the adder boost. And does it do well? To our surprise, we started a very simple smoothing spline estimator, fixed width. So we're not tuning any parameter, just keep fitting residual. In that case, you have a very easy closed form derivation for the bias and variance. And we show that depends on you choose your stepping time, you can adapt to the underlying smoothness of the Sobolev class. Sobolev class is like first order derivative, second order derivative. And boosting has this amazing property that without knowing what's the smoothness underlying the class, it can adapt. And statistical, we do have procedures too to do that, which is through wavelets and some blockwise thresholding. You look at the history, about the non-parametric stuff. It's really very recently we're able to do that, to automatically adapt to the underlying smoothness. And it's kind of a little hacking job compared with boosting. But there was a similar result for Gaussian kernel support vector machine by Lin and Brown, show exactly the same thing. For Sobolev spaces, and you do a Gaussian kernel support vector machine, automatically, if you choose your sigma right, automatically adapt. So somehow these two classes of procedures traverse all these optimal points for these different smooth classes without having to, kind of block things. And, it's a little, it's smoother. So that was a surprise and that kind of convinced me that there is a connection between computation and regularization. But again, there's no general result on how exactly you should connect these two. So what's boosting? I'm going to tell you the L2 boost because it's the easiest. And that's what connects to the BLasso, or the lasso. So you have a p-dimensional predictor xi, and yi you can think of just a continuous response. And could be classification too if you take L to be the exponential loss function. And our algorithm later I'll tell you also apply to exponential law. It doesn't just apply to L2 loss. And the version I will compare with is so-called the forward stagewise fitting boosting with a fixed step size. So what you do is that you have all these p features. At every step, you're going to look around for a fixed jump from the current position by plus or minus epsilon each direction. And you're going to jump to the direction, only 2 points you are searching, not continuous search, where reduce the loss function the most. And then you take that step. So it's a discrete step, discrete search. You understand what I mean here? Yeah. So it's a version of boosting. It's not exactly the continuous line search version.
So that is the purpose to estimate beta, right?
The beta is your parameters. It's the kind of loadings of your features.
Okay, so this procedure of estimate beta, so it's not maximum likelihood, it's just the what?
This is basically a fixed step gradient descent.
For the objective function?
Yes. So this is totally not likelihood based at all.
So in that case, when you talk about the loss function,
it's L, the L. For example,
but every time we talk about loss function, we talk about discrimination. You get the classification problem. If you make mistake,
but it could be L2, so that would be regression.
Oh, I see. Okay, so
yeah.
Okay, so
either way, it would be. It could be logistic. I mean, any convex usually that's what.
So the residual error square. That's
that would be the loss function. Yeah.
So in this formula, you assume the loss function is a convex function.
Well, yeah, that's what I mean. But to run the algorithm, you can run it. It might not work.
I can run it.
Yeah.
If I run to understand
Yeah, you might have, depends on the starting value, you don't know where you'll converge. So all the theoretical result on boosting assume convexity.
But in that case, since your dimensionality is fixed, beta, is fixed, then so why is that method better than maximum likelihood method?
For some cases, it might not be better, but for the other cases, if you care about the number of errors, your L is more connected to that. It's more zoomed in to whatever the loss function you care about. Maximum likelihood is like going into a different loss function, which is the likelihood, like Kullback-Leibler divergence type of thing.
And also in this, you have minimum mean square error estimate.
Yeah.
And then in that case,
that would be the L2.
The L2.
Yeah.
So if you do that kind of estimate, why isn't that better than this boosting method?
Well, the minimum depends on how you solve that optimization problem, right? So this is a particular way of solving the L2 problem. This is a gradient descent way of solving it. You could use Newton method. You could use Hessian inversion. And that, we try to say that it matters how you solve the optimization problem.
So the objective function is the same, but different techniques.
Yeah, and then you stop early, so you're traversing different paths.
Okay.
And you use cross-validation to stop, so the result could be different.
But before, I always thought that every time you use the boosting, you don't actually constrain how big the model is. So at the end, you actually estimate parameter as well as estimating the order of the parameter in terms of P. So P here is fixed rather than variable.
Well, you could make P variable too.
Okay. And then the algorithm automatically.
Well, so in the minimization step, I could involve another inner loop optimization to make it infinite dimensional. Right now, I'm not doing that. I'm doing fixed number of features.
Okay.
Yeah, but you could. That's one thing nice about boosting and this gradient, that you can have an inner loop optimization, so you can have infinite precision to select that. Right now, I'm doing a discrete version.
Okay. So if that prediction function is linear, then does that algorithm give you the same solution as the standard linear regression, result?
No, not if you stop early.
Okay, so that's not as good as the linear method, huh?
No, because sometimes it's high dimensional space. You don't want to do the linear method. You don't want to do the OLLs, ordinary squares. It's overfitting. So that's the whole point. You stop early, you regularize.
Okay.
So ridge regression, right, is explicit regularization. And this is implicit.
But regularization depends on how big your regression terms are.
Yes, but you can stop early. If you have more, you might stop even earlier than others. So that's the parameter you're tuning now.
Okay.
If you let it run to the limit, you basically, if the matrix can be inverted, right, it's ordinary squares.
Okay.
Yeah, but now you stop early, so it's a regularized version. But there's no closed form like ridge regression.
Okay.
Yeah. And then Brett Efron, there's a discussion paper, the Lars paper, they observed a striking similarity between boosting, I told you, and something else already existed in statistical literature called Lasso. I'll tell you in the next slide. So they observed that if you do boosting with small steps, the path, which means that when you change the, if you look at the L1 norm, and you fit more, the L1 norm will go up. The two paths are very similar. Okay? And what's Lasso, which I haven't told you?
This is for L2 loss function.
Yeah, this is for L2. In their case, for L2.
Have you ever tried it?
There's some generalization by Ji Zhu and people like it to exponential loss. They observe similar phenomena. Yeah. So I take it it's kind of general.
Okay.
There's a similarity. So Lasso actually was about the same time as the ADA boost, was invented by Ralph Tibashirani right now at Stanford. And I mentioned ridge regression, right? Ridge regression exists since the 70s. So you recognize that you don't want to do least squares because it's overfitting, or for numerical stability, you want to penalize with a L2 loss, L2 norm, right? But here, because the duality, you know that if you do the penalized version of least squares, it's the same as doing least squares subject to L2 constraint. And Lasso says that you don't do L2 constraint. That will lead to a closed form ridge regression. You do a L1 penalty. So L1 penalty corresponds to this diamond constraint. And when you have optimization which is quadratic with like this sharp edge, a lot of times, not always, your solutions are on the vertices. And when the solutions are on the vertices, you have sparsity. Basically, one of the feature coefficients are set to 0. So indirectly, you are selecting now features. Ridge regression, you shrink, but all the features are still used. And this way, you actually make some of the feature to 0. Because what could happen is that I could the minima here, then there's no sparsity. But because you can imagine that randomly there's this sparky stuff, most of it you're going to hit here a lot of times. It's not guaranteed every time you have sparsity, but a lot of data you do have sparsity. In high dimension, you have this very sparky stuff, and you have a ball, most likely you will hit the vertices.
But that optimization is just a standard regularization. But
yes.
You regularize to make sure the B isn't too big.
Yes.
So how does that differ from everything that we read in neural network? You do regularization.
Well, the good thing about this regularization is that it comes with it the sparsity. So it does two things in one hit. It's like one stone, two birds. You have regularization done, you also have sparsity. Sparsity for interpretation or extrapolation is very useful. You want fewer terms. Suppose I give you two models. One has 10 terms, one has 100 terms. They give you the same prediction. Which one you choose? You want the 10 terms.
Yeah, but that's already done by beta term, the second term.
It's this particular L1 loss. If you do L2, you won't have that sparsity.
So in other words, if you do L2, you get more non-zero parameters.
Yes. Because if the solution here says that, well, beta 2 is 0.
Okay.
Right?
Okay.
So in high dimension, you can have lots of zeros. And you have a smaller model. It does regularize, but also give you the sparsity.
The sparsity, can you explain sparsity again?
Sparsity just means that you have many features have 0 coefficients.
Oh, I see. Okay.
So you have smaller models. Remember the model selection is about choosing features? So this one, you choose the feature indirectly.
No, but feature is done already. Z is the feature, huh?
No.
So X
is a feature.
Is a feature. But that's given.
No, because remember I'm doing gradient design from 0. I'm picking one at a time. I don't have to include all of them.
I see. You may throw out.
That's what I was talking to you.
Okay, this morning. Okay.
Yeah.
Okay.
So you don't have to have all of them.
I see.
You do have the possibility to have all of them. For example, if you end up minimized here, you got all of them.
You still have the feature, the pool of feature available.
Yeah.
You just decide which one you
Exactly.
throw.
Exactly. That's why it's good about boosting. For kernel machines, it's a little harder to do that.
Okay. But
Right.
also practical problem is how do you get the pool to begin with? That's even more problem.
That's a subject matter.
Okay.
That statistics cannot really answer. That's why you need to talk to the experts. Statistics cannot answer that question. Then you guys won't exist, right? If you can answer that question.
Okay.
Right. So we kind of have some general methodology can be used, but that's the hard question. That's why I said for the remote sensing, right, we basically have to start from there by talking to people. Yeah, that's very important. So traditionally, people just solve Lasso by quadratic programming. And then now it's very obvious, it's very wasteful because for each lambda, it's a quadratic programming, and they do for a grid search of lambda and then do cross-validation to select a lambda. And now, of course, we realize, for different lambda which are very close, you shouldn't do the quadratic programming twice, right? They're very similar. But that's the original, like what's the second generation, we just throw it into a quadratic programming and let it solve it and throw it again.
Yes, so here you're talking about absolute sum as the regularization term rather than the regression term, the error, the residual error itself.
Right, I'm talking about this.
I see.
This is still L2. I don't have a...
But L2 sometimes is not good either because it doesn't deal with the tail, the distribution of the error.
Yes, you can do L1 there, that's fine.
Okay, but that may not have the property that you're talking about.
No, still sparse. Still sparse. So the loss function, we can do any convex here and there. Yeah.
Okay.
So L1 is okay, that's the robust regression, right?
Okay, yeah.
So as I said, so now this Lasso gives you this kind of model selection results. So and it's easier to do than the combinatorial search. So the question I want to address is whether it can actually select the correct features in the classical setting. In the setting that you have a true model, life is good, you have the true model, you got everything, and P is small, N goes to infinity, the classical setting. Okay? And assume that my design matrix X, so the first Q features are the relevant ones, and the last P minus Q are the irrelevant. right? You store it in anyway, so would you be confused? Can you pick the right ones? And this is some typical regularization conditions. And there's an earlier work by Knight and Fu showing that if you look at L1 distance between the estimator through Lasso, if you properly choose your lambda, that L2 distance is consistent. But that it doesn't address the non-zero components consistent now, because you can have a tiny bit 1, never 0, but L2 is OK. So we're going to look at from the 0-1 loss, whether you pick the right ones. I mean, their work is very bad. So we define this model selection consistency, saying that you basically, the non-zero ones is the same as, this is the true parameters. This is the estimated. Okay? So this means that you pick the right ones. And with the estimation consistency, we only need to look at the sign. And this is saying that it's stronger. You want not just the non-zero ones match, you want the signs to also match. Okay? Because you can pick the correct ones, but the sign switched. And we make it stronger. Just mathematics is easier. And we have something called strong sign consistency, saying that you have a fixed lambda, doesn't depend on data. When this go to 0 in a right rate, you have the consistency. The other one says that it's a general condition, saying that you can choose this stochastically, depend on the data, and make it consistent. Because in the data, you're going to search for lambda and depend on data. So if this holds, this holds, but this holds, this might not hold. This is a more stringent requirement. You want a fixed lambda n.
So here by model selection, you mean the size of the beta?
I want to choose the right non-zero ones,
Okay.
the size.
Okay, another word.
Not just the size, but also the right ones. You can have the size right, but the wrong features, right? For example, the true model is 5 features. I can get 5 right, but the 5 wrong ones. I'm asking the dimension and the 5 correct ones being selected.
And also, in this case, you're talking about linear regression.
Yeah, this is a theoretical result. I'm assuming life is good, everything is the right model. It's only some irrelevant, but in real life.
But in real life, the more probable issue of model selection will be whether you do linear regression or quadratic regression.
I agree. But here, just saying that even in this case, whether Lasso will work.
So, okay.
Right?
So does Lasso generalize to this different kind of model?
Yeah, right now I'm assuming the basic, very classical case that is everything's nice. We know that model selection will select the right models. So now you made the computational shortcut. Would you keep that property? I mean, general model selection have that problem too. When the model is wrong, that it's very, depending on how wrong it is, the result will be different. So we basically came out with almost like necessary and sufficient condition. Depends on the design. So the X1 is the design, is the feature columns which are the relevant ones. And X2 are the features which are irrelevant. So if you forget about the sign, because the sign in real life you don't know, so you might just want to remove it, because it's depending on the true model. You're basically asking that this is basically the regression coefficient of the irrelevant ones projected on the relevant ones. The coefficients cannot be too big. In some sense, the irrelevant features cannot be too similar to the relevant ones. If they're too similar, you cannot tell them apart. Okay? At the high level, everybody probably thinks it, but it's just like really pinning down the exact form. If the two correlated, the relevant, how can you tell them apart, right? You're going to mix them up, because from the linear regression point, they're exchangeable. And it's really pinning that, we think we can do it for the P large case, but that's not that. There's some related work in the other setting. But so as I said, because the beta is the true one, if you know the true model, you really say this should be true. Doesn't matter what the signs are, right? Look at the design. And then that will make it to a simpler condition, only to do with the design. So, and you can verify that if you have a constant correlation for all your features are symmetric, then that will satisfy. And if you have this decay, exponential decay correlation, you have bounding correlation, it also satisfies. But look and see that the bound, Q is the number of irrelevant features. When Q is very large, this condition says that your correlation has to be small, which is also sensible, right? When you have lots of them, if they're really highly correlated, you're not going to be very. And there's relationship between this condition and something by Donahoe from very deterministic point of view, from linear algebra type of stuff. So the idea is that you want things relative to be independent and cannot be too many. So what we did is that this is special cases. Suppose you just do IID, Gaussian, independent, and with the same P and same N, we simulate it and see how often this condition is satisfied. And you see that when Q is small, right, this case you can prove if the true dimension is 1, you can show this is always satisfied. And then you can see that a lot of times the condition is not satisfied at all. We just want to make a point that you do sacrifice doing this computational shortcut in terms of consistency. But we think this can be rescued. So what you can do is that you use BLasso to select pre-select the features and then run a model selection. That will be a much smaller set. So you do a little bit combinatorial search, but much smaller possibilities. Because BLasso, because of the night and full result, will always over-select, never under-select, under this scenario. And therefore, at least can be rescued.
You mean that BLasso can be used as a feature selection method with other feature selection methods together?
So what you do is that you use a lasso, different version, whatever, how you do that. And you say from your 1,000,000 or something, you select like 500. And then you do a combinatorial search on, or like a stochastic search, go and say BIC.
So it's like a
pre-selection, yeah.
So in order to make the pre-selection successful, you come up with the concept of consistency. You see, the more consistent the
Sometimes BLasso itself is consistent, but you can see a lot of time it's not.
So let's put it this way. Let's say we have different algorithms.
Right.
5 algorithms, and the BLasso is one of them. All these algorithms can be used as a pre-selection method.
Right.
How do we choose the best one? Is there any measurement?
That we haven't addressed yet.
So, do you think the consistency of the algorithm?
This is not algorithm. This is a lasso solving exactly.
Okay.
The analysis on the lasso.
Yeah, this is solving lasso problem exactly. This is a very theoretical result. It's more addressing when you switch to a combinatorial search or convex optimization, do you lose anything?
Okay.
From the model selection point of view, and you do lose. But that can be rescued. But we're not addressing how to solve lasso. Yeah.
So do you generalize that problem from regression to classification?
No, our algorithm, for our result,
yeah.
This is totally
regression only.
True.
Okay. Oh, okay.
Yeah, I think we probably can do that, but yeah, I think it's possible. But the condition will be, that's a good question. The condition will be some weighting. It won't be just the design matrix, because the exponential loss locally will be weighted squares. So that weight will have to come in. I think some result, I'm sure, can be proven using a weighted condition like that. Yeah. But we haven't done that. So coming back to how to solve lasso. So lasso is not perfect, but still lasso is pretty good. I want to remind you again that there's a striking similarity. So the question is, do you have to go through quadratic programming to solve lasso, or you can go through the boosting route? That's the second part of the talk. So they observed in the last paper by Efren et al. That they're similar, but they're not the same. And what we did is that we added the artificial, this is like 10 features, we added the 11th feature, which is a linear combination of 3 of them, and with a little random perturbation. We added that to the pool. And then we run boosting and we run lasso through quadratic programming, and suddenly you see very obvious difference for this correlated one. So in their last paper, they showed that under certain conditions, L2 boosting and lasso will give similar paths, but those conditions in this case are not satisfied. And in high dimensional case, I want to argue that this correlation is very strong, right? A lot of features, a lot of more strong. So most likely, boosting is not solving lasso. Boosting could be very interesting, very useful in its own right, but just not lasso, right? It's going through a different path. It could be itself very interesting, might be more useful, but it's just not lasso. That's what the point we want to make.
So you cannot make sure that lasso is better than boosting.
There's no result saying that. Yeah, it's only so far. That's why we're comparing, right? So far, because the way we solved lasso, right, you can see the problem most time will be better because you.
In this case, you only assume that lasso is good, and we want to approximate lasso as much as possible.
Yeah.
And the boosting cannot do that in certain cases.
Right. We're not saying that lasso formulation will always give better result, but you can see empirically that the two algorithms are so close that most time you're not worse because you're taking all the boosting steps in the way we solve it. Right.
So this curve shows the error objective function?
No, show the path. This is the coefficients for different features, and this is why I increase the L1 norm.
The L1 norm.
Yeah.
Okay, so different.
So when the L1 norm getting bigger and bigger, basically you're removing the L1 constraint. Eventually, you converge to ordinary squares.
Oh, I see.
For this problem, because it's a small data set.
Okay. So now in that case, I think the comparison will be if you just do the gradient descent.
Yes.
How would that end up with? Is that going to give you some similar?
Yes, that's what I'm going to show you. Basically, that the BLasso algorithm simply gradient descent.
Yeah.
Exactly. But not on the L2 loss. It's on the penalized L2 loss.
Of course.
Yeah. So it's yeah, exactly. It's not a. So that's the second half. So if we do a gradient descent on lasso, and lasso has two parts: the loss function, which could be exponential, which could be L2, and then L1 loss. And if you do a gradient on a fixed grade, then the L1 penalty will only change plus epsilon, the step size, or minus epsilon. So the penalty change is very easy. And then if you just want to do gradient on that, you want to do the forward step to reduce the loss function, and the backward step might reduce the penalty. So the result is that sometimes you do want to take backward steps. But we came to the backward step not through this formulation. What we did was that we're working with a hedge fund in San Francisco, and the firm has a criterion, do some stock prediction based on these squares. And I was asking Peng to try to see boosting, and he being, he's very smart and saying that, well, of course, we shouldn't go from zero because the firm is making money based on these squares. We should do backward, right? We should just move away from these squares during reduction. And later, he discovered actually we can motivate the backward steps through the lasso. But that motivation actually is useful is that for time series context, you often already somewhere at time t, and when you're at time t plus 1, you don't want to boost again, right? You want to revise a little bit, then go forward. So it just makes things very flexible for revision, independent of the lasso. So the backwards is very much needed. I'm saying that on the top of boosting, we're just motivating it through the lasso, and that's become BLasso. But in general, I think backwards they are very much needed. And if you look at classical regression in model selection, we always have forward selection and backward selection. So people know that you have to go back and forth.
So in that case, if you were to use gradient descent, you will lose the opportunity of selecting data.
What do you mean?
Gradient descent actually makes use of all the pool of data.
No, we're doing component-wise gradient descent. I'm sorry,
Okay.
We're doing one at a time. So we first select the direction and then do a descent. We don't do the
batch.
Yeah.
Okay.
No, we don't do the linear combination of directions. So it's component-wise gradient descent. I should emphasize component-wise. So we can show that, if you take lambda 0 this way, that's big enough. Okay, because when lambda is infinity, you know the solution is 0. But you can show that this is big enough lambda to start with. And for you always take a first forward step. And at any time, you look at all the features you already selected, and you say, does any of the back step help me to reduce the penalized loss function? If that's the case, take the backward step. Otherwise, take the forward step. After you exhausted all the minimization at the resolution of epsilon, you move to the next lambda. Okay? So this way, actually, you don't guarantee the lambdas, the L is always decreased. Because it's not, it's a fixed step. So sometimes it might come up a little bit. And then you run that algorithm with the small steps, and you can see the BLasso this is boosting with backward step, produce exactly lasso. Okay? Which, is gradient descent on the right loss function, or convex, small step. And we can prove the convergence if the steps I go to 0. Well, how do I do with time? Oh, I have it there, sorry. So I just want to point out that it doesn't have to be, the loss function doesn't have to be L2. It can be the Hinge loss function. This is a very classification, right? And the theorem doesn't quite apply because we need but the algorithm runs. Okay, in theory, something could get weird, you kind of oscillate. But in practice, so they basically did the last version of that, and we can run our loss version.
So the reason why you use a Hinge loss function rather than sigmoid loss function is because you want to keep the
You want convexity.
Everything.
Yeah. This is basically Hinge loss from support vector machine.
That's not very good in actual classification.
No, it's pretty. I mean, if you want the convex one, it's pretty good.
No, not convex one. So if you actually have sigmoid, that gives you more realistic error count.
Yeah, but then you have a harder optimization problem. So it's a trade-off, right? If you get lucky.
Gradient descent.
But gradient descent, when you don't have a convex, you might be in a local maxima or minima.
Okay.
So you have to start menu, and then you have to pray that you get the right one.
We actually use this one.
I see.
And then happy with stacking to local optimum. But we never tried that one. Probably it's a good thing to try.
The thing is, with a problem, you have a lot of experience, right? You usually have a pretty good starting point, so you're okay. But if it's a new data set, that's where you have, you want something which you know there's a unique optimal. And you can switch back and forth. So we also show that you actually can have other kind of penalty. You have L1 loss, L1.1, and L2, L4, L infinity. And we quite like that L infinity. That's the paper we're doing now. Is that L infinity now actually forces all the coefficients being the same. So that's basically putting group structure into the features. That's what we're working on paper. So under this kind of penalized optimization framework, how can we work in some structures of the features into this framework? We do a combination of L1, L infinity, and other loss.
Structure you mean the number of clusters, or it's a hierarchy?
In the paper, we're writing have both. Yeah, I don't know how flexible in terms of hierarchical structure, but we could work that in.
So to this experiment, you only use BLasso.
Yeah, we use BLasso. So the good thing about BLasso, as I said, the lasso case, there's a paper by Lars algorithm. It's piecewise linear. It's very fast. I'll come there the next slide. But BLasso is you don't have to, but it's a lot of work for special loss functions. BLasso is for any loss function you can write, might take longer, but you don't have to do a lot of hard work by the brain.
So it seems it's very true to just modify the L1 penalty.
You actually don't do derivative either. You take a difference, right? Mm-hmm. So it's very easy to run into a module. It might take a while, but it's pretty brainless in the sense of you don't have to fine-tune for different loss functions.
I already implemented the L1 case. So if I want to implement L2, L4, and L4,
yeah, it's very easy. Yeah, you can actually
use the same algorithm.
Yeah, you just have to change that part.
Okay.
No, it's a little different. L1 is a little different. L1 is the penalty actually will only change plus epsilon and minus epsilon. If you look at our paper, we have something called generalized BLasso. Yeah.
Okay.
So Lars, which I mentioned in the paper, but what they did is that for L2 loss function, L1 penalty, they have a very sleek way of generating the whole path. In that case, the path turned out to be piecewise linear. So they were just looking for kinks and generate the whole path. But just like everything, we discovered, they knew it, but that there was an earlier work by numerical analysts by Osborne and his co-author, something called homotopy method. Was kind of buried, at least statisticians didn't know, it's basically the same thing. But so the Afrin paper calls it Lars. And there's extension to Hinge loss function, but each individual case you have to work out the algorithm itself. It's piecewise linear. So it's not just L2. And how infinity will work out the details, you can also say it's piecewise linear. It's hard to, this is only work for piecewise, for fixed features. So if you want to feed a stump with infinitesimal cutting point, this one won't do. You have to basically discretize and do it that way. And it's hard to be adaptive. When the data changes, you have to rerun the algorithm because it's very batch, right? The whole thing is a piecewise linear thing. So it's fast, but it's not adaptive. Boosting can deal with different loss functions and also can have an inner loop of optimization, therefore can do infinite kind of predictors, but could be greedy and not always a good approximation for Lasso. And adaptivity is limited because you think about it, it's only going forward. If you want to come back, if things change, non-stationality, you don't have ability to revise. And BLasso is kind of have a lot of advantages of boosting, but also have this nice connection with time series. And also, after we did BLasso, I looked into the statistical, the optimization literature, and it's very similar to the barrier method. Basically, solve the whole sequence of the optimization problem in one hit, right? Because I need to solve for different lambdas. For each lambda, it's an optimization problem. And the game is really that you start your optimization for the next lambda from previous solution because they're very similar. And that's exactly how barriers method work. So barrier method is convex loss, convex constraint. They turn that into a penalized method. And then they have similar way of outer loop and inner loop. Okay? It's one of the interior point methods.
Is it semi-definite programming method?
What?
Well, there's a very popular method called semi-definite programming.
No, it's a different thing. The constraint is quadratic, I think, semi-definite programming. And I just want to make a point about statistical computation being special in the sense that compared with numerical optimization, that's why we don't need convergence, is because our objective function is a random quantity. Next time will be different, so don't take it too seriously because you don't need that precision. And even in parametric estimation, there's a result saying that if you start with something like a method of moments, you only need 1 Newton step, and then you have statistical efficiency already. So you don't have to derive many, many Newton steps to go to convergence. You don't need the convergence. And in non-parametric estimation, of course, you also don't do exact optimization from the start. You do surrogate loss function, and you have different ways of regularizing, and you rely on the test or object, validation to stop. So there are many room for you to do different regularization. Depends on the requirements. So to summarize, I hope I convince you that Lasso is not a bad computation physical alternative, even though it's not always consistent, but you can kind of do some remedy to that by doing a post-processing of model selection. And BLasso has a nice connection with boosting, but the new step of backward is very useful for revision of the model. And they only use differences. It doesn't take derivatives. And we do have the approximation of BLasso to the Lasso path. And the generalized BLasso deals with general loss function, general convex loss, and penalty functions. So what we're doing right now, as I told you, we're working on some Lasso with kind of composite structures, basically building some feature structures, and students making this distributed online setting, also time series. And we also want to stop the algorithm, especially for the online setting, without using cross-validation. In terms of applications, we work with a neuroscience group in Berkeley, and they basically have they call response function estimation problem. They have this natural stimuli like sounds or images, and with a subject like macaque or songbird, and they want to relate the neuron firing rate with the input, which is natural stimuli. And they report that it doesn't make too much difference from boosting. And the reason is that their data is very low signal-to-noise ratio. So after the forward steps, your data doesn't support any backward step because you cannot really tell their fine structure. But some recent work of Jianfeng and Sumi, they show that, I'm also on the paper, but really their work, that when you have large amounts of testing data to be able to tell these fine features, then you do see backward step helping. After the forward step, the major features get taken out. But for later fine-tuning, the backward step is helpful because you can come back a little bit from the major features and go forward on other directions. And this huge test data really can show the finer difference. And the Stanford group, they told me that they like the connection with Lasso and boosting, but they feel that in practice won't make too much difference. So Hasty Tibetronics group. And I see where they come from, that for a lot of, unless it's huge test data, like the neuroscience data, you just don't see the difference because you don't have the fine structure of the kind of the differentiability in the data to tell apart the fine feature. But for this IME, is that called IME? You call IME?
I would call this
IME and this index method editing task. Input. So basically you have phonetic strings of Chinese phonetic string or Japanese strings and you want the character to be returned. And in that case, you have huge, we see like 0.5% improvement. They translate to about how many? It's about 25. How does it translate in terms of character improvement?
Yeah, that's character error.
Yeah, character rate. So for the huge database, it's still because the accuracy is already 97%, right? So it's where you see the fine-tuning. And there's some other works I did with Microsoft Research Asia, with checking some modification that there might be some multi-class classification. It's also could bring some. We haven't seen any worse performance than boosting. So that seems to be the case. So it seems like the complexity is not more, it doesn't hurt. And in some cases, it does bring improvement. And so now you know you're solving a global optimization problem. With boosting, you can see that it's solving a local Lasso problem. It's like a stochastic descent version of that. Yeah.
So can you say a few words about the structure of Lasso that we talk about this morning, which we didn't go through?
What do you mean by structure?
The structure, what? You talk about sequence.
Structure feature.
Oh, the structure.
Features. Is that related to this? But that may.
Yeah, basically we now design a different loss function, which is a mixture of L1 and L infinity loss. We group them and put L1 inside and then put L infinity outside. So it's still convex penalty. So BLasso still works, but because the way you construct the loss penalty, the penalty you build in structures, and then we can also have some hierarchical structures in there. So basically, we're thinking that for this huge data problem with so many features, L1 a lot of times is not enough. So you need more knots so that people can put in more prior knowledge into this framework of penalized optimization.
Yeah, I'm thinking of are there any empirical benefit of having this feature structure?
Well, for example, we started with a graphical model problem where you do pseudo likelihood. And for each link, you can have two ways of characterizing it. And of course, they should be zero and non-zero at the same time. Right now, people just say if one way is zero, we say it's non-zero. But you can also put a constraint saying that the two parameters should be zero and non-zero at the same time. And then, as I said, in the gene expression kind of analysis, you can think of that, the genes, suppose you want to predict cancer, you want to see what genes are kind of related to that. If you know certain genes are on the same pathway, you might want to say that they are in the same group. They should be all related or they should be all out.
Sometimes people try to cluster features in groups so that when in the case there are not enough training data, we can still do it pretty good. So in your case, I don't know how much training data you need to
how many what?
Training data.
Training data?
You need to capture the structure of the features.
Well, I think, I don't know. The answer is we just, we have specific cases, just like the BLasso, right? We're in the more methodology stage. We have to try down real data and some more simulations. We're still in the middle of doing that. So the idea is that you should need, because this type of penalized optimization also has the Bayesian interpretation, right? So in a way that you try to build in more information, so therefore you can, hopefully you need fewer samples for a more complex structure. At the high level, that's what we hope for. But we are still very much in the simulation stage and haven't tried on real data yet.
Yeah, I just, we did some work like a word cluster. In order to predict the probability of network, we try to group the word in the conditional part.
Right.
Let's say, and the cluster is generated with respect to maximum likelihood criteria.
I see.
So sometimes the cluster is not optimal because our evaluation metric is error.
Right.
So in your case,
Oh, you said what if the grouping structure is wrong?
yeah,
We did some, again, only simulation. It has some tolerance. It doesn't have to be exactly right. Of course, it's totally wrong. It's not a good idea. It would be worse than Lasso. So we're comparing with Lasso without any structure.
so my question is, in your case, the cluster, is there anything to do with the cluster with the objective function in the loss function? If you have different loss function defined in the Lasso models, can you come up with different clusters?
Yeah, we're not worrying about that yet. We're very much in L2 and then different L gamma now. But that's a question. You might have to weigh. My Hinge said you have to weigh the weights differently for different loss function. Yeah.
So can you go back to the Hinge function slide, which I think that's the one slide to get the way you convert the problem to classification. So when you do that, so you have the same regression term there.
Well, you have the same difference, but then you're not putting the difference through L2, you're putting through a Hinge loss. Hinge loss is like that.
Okay. And then how does it convert the problem into classification? So you get the loss function like this. So the boundary starts from where the curve starts.
Well, people have shown that if you choose lambda properly, there's some results showing that.
It's not clear how that turns the problem into classification. The classification problem is that you have separate classes.
No, this one too, you basically have a decision rule based on this. If this is larger than 1, you do something. If less than 1, you do something. Yeah, you have a decision rule right out.
Okay.
Yeah.
Okay. So when you have this Hinge function, all it says is that if that term goes below this,
Right, it's 0.
you have very different
Loss function,
thing.
yeah.
That's
Yeah.
not very realistic.
Why not?
It looks like if you are doing correct, you get this. You don't get penalty.
Right.
If it's wrong, you get
Right.
very heavy penalty.
Right.
The further away,
Right.
the more penalty you have.
Right.
And that's not realistic because if something is really wrong, you don't care. I mean,
But
there's no
usually
hope for you to
the
get
thing-
it back. There's no hope to get it back. Why don't I just make it wrong so that it won't affect the cases?
Most of
where
time,
they're close to
most
the
time you push because it's that you push back to something close to 0. You're not operating in that domain.
But the thing is that you might have outliers, right? For those outliers, you don't.
But this
really
is L1. If his term is better than L2, this is a linear thing.
Oh, I see.
So-
You may protect yourself by doing this L1.
Yeah. So this is for classification problem. This is definitely better than the L2
I
loss.
see.
Yeah. So of course you want, if you want to, yeah.
Well, there's no way.
People can show that Hinge loss is kind of in some sense, the closest convex optimized like upper bound for the 0-1 loss.
I see.
So it's the smallest kind of convex upper bound.
Okay.
So if you want the convexity,
That's not the only one.
yeah, you have to. You cannot do better.
Okay.
But of course, you say you don't care about convexity, then
That's different.
that's a different story.
So
Yeah.
you said the theory doesn't apply precisely. It's because you get this continuity in this loss function.
What do you mean by theory doesn't apply?
I mean, I think you make a comment when you talked about this earlier, 10 minutes ago, that
Oh, because
you have some problem there.
the problem is that to prove that my epsilon goes to 0, our algorithm converts to the theoretical path, we needed a second order differentiability to be bounded away from 0. And this one, that part, that's where things can
In
get.
practice, you want that.
In practice, you can imagine you can cook up some contrived example that this will be.
So maybe you can do this something like this, gradually moving up.
Yeah, so you can smooth it a little bit. But in practice, I don't think there will be any problem. Yeah.
So actually, I have a question for Jeffrey. How do you convert the IME problem to classification problem?
Okay. We actually use a trigonometric language model to generate the m-best given an input hypothesis. Then you can formulate IME as a ranking problem.
Okay. Okay.
You can use that in your problem.
That's what I'm thinking of.
Yeah.
So you need to get an inverse.
Yeah.
Any other questions?
Let's thank to speak.
Thank you.